Next speaker is Paolo Leonetti, who talks on independent families and asymptotic density. So, please.
Thank you, Mel. Um, I put it in a small image. I hear some echo. No, okay, that's fine. Um, Today we'll speak about something which is not really related to number theory, except that we are speaking about asymptotic density. This is a joint work with Jonathan Cate, which I just saw. He woke up and is listening us. So, okay. So let's remember the classical definition of independence for independent families of natural numbers. Now, first of all, I define a notation which is quite common, which is the following. Given a set A, we define a to the power 1 to be a and a to the power 0 to be the complement of a with respect to the natural numbers. And we say that this is a classical definition. A finite family from A1 up to AN of subset of naturals is said to be independent if whatever is the exponent here that you can choose, epsilon 1, epsilon 2 up to epsilon n, then all possible intersections are infinite. This is the classical definition of independent family of finite family. And what happens if the family is an arbitrary family, potentially infinite? An arbitrary family, subset of the power of n, is said to be independent if every finite subfamily is independent. So, this is the classical definition. I'll just give you one example. If you take every prime p, and for every p prime, we define ap to be the multiples of p, then you can check that by the Chinese remainder theorem, then this family here is a countably infinite family, which is independent. So the first question that comes to mind, but this is also well known, is does there exist an uncountable independent family contained in the power set of the naturals? Well, theorem.
Oh, excuse me, Paolo. What
Yeah,
does it mean when you raise the set to the power 0?
that's written here. To the power 0 means the complement.
Sorry. Thank you. Okay.
To the power 1 is the set itself. And thank you that you asked it, because we will use this notation up to the end. Okay, first theorem, there exists an independent family of cardinality continuum. And there are many proofs, known proofs, and this one is due to Gowers, and it goes as follows, that they are just the main ideas, but more or less we need just to fill the details. It is just pick a set of irrationals which is linearly independent over the rationals, and we know that there exists H, calligraphic H, which is of cardinality continuum. And we know by the Kronecker theorem that whenever we pick a finite subfamily of calligraphic H, then the multiples of this R1, R2 up to Rn is dense in the k-dimensional torus. Now, that's the classical Kronecker theorem. It just requires the linear independence of the rationals. And so what is the family? For every R, which is here, this is a typo. Now we are in the iPod, so we can correct it. For every R which is in calligraphic H, we define AR to be the set of naturals for which NR has an integer part which is even. Now you can check that this is really an independent family, and since H can be chosen to be with continuum cardinality, then there exists an independent family of cardinality C. But first question, why this notion is called independent? Well, this goes back to the independence in probability. So let's try, this slide is well known to everyone who did one course in probability. Let's pick a probability measure space. So F is a sigma algebra subset of capital omega, and capital P is a sigma additive measure on the sigma algebra calligraphic F. Then we say, that's the classical definition in probability, that two measurable sets are P independent with respect to P, if the probability of the intersection is equal to the product of the probabilities. And note that since we have sigma algebra, then it is stable under intersection. Well, that's trivial. Now, you can check directly with this definition that if the family AB is independent, not only you have this property, but that's really the first exercise in probability, the probability of A complement intersection B, if you want A to the 0 intersection B to the 1, is equal to the probability of A complement times the probability of B. So here, this implies just changing the exponent, repeating this reasoning, which is really elementary, that whatever is the exponent here, epsilon 1 and epsilon 2, then the probability of the intersection is equal to the product of the probabilities. Now, even this is a simple exercise, it reminds the definition of independent families, the classical definition of independent family of naturals. But looking at this last line, this suggests that not only the intersection has to be infinite for subset of natural numbers, but here we are quantifying how large is the intersection. The probability of the intersection is the product of the probabilities. Fine. So what's the idea? The idea is try to pick an independent family of naturals and replace this P with the asymptotic density. So let's formalize it precisely. Let's call calligraphic D to be the family of sets which admits asymptotic density, which means the limit of the ratio up to n divided by n exists. And the asymptotic density is denoted by D. D of a set is equal to the asymptotic density of that set whenever it exists. Now, in place of the probability space omega of P, we consider, let's say, the triple power set of n, family of sets calligraphic D, this D here, which have asymptotic density together with the function D. Is it a probability space? Not in the classical sense, meaning that the properties are weaker. And that's well known that D is not even an algebra. It is stable under disjoint union and complements, but not under arbitrary unions. And moreover, D, which is the asymptotic density from calligraphic D to the reals, is a finitely additive probability measure. Okay, so that's just a bit weaker than a probability measure space. Let's go to the main definition, which is here in this slide. A family of subset of calligraphic D, let's remember this is the family of sets which have asymptotic density, is said to be independent with respect to D if these three properties hold. Property number 1, the asymptotic density of every member of the family is strictly between 0 and 1. It is neither 0 nor 1. Second, the algebra generated by the family calligraphic A has all the elements which have asymptotic density. And third property, which is the one that we expect, the density of the intersection is equal to the product of the densities for all finite subfamily of the original family script A. Now, this condition here reminds the definition of independence in probability. Not only it reminds that one, but we can check directly from this definition, this is just a few lines, that analogous in the similar way that we do in probability, the same exercise proves that we can add the exponents here in the way that we like. And we obtain that the density of the intersection, whatever is the exponents, 0 and 1, on the finite subfamily, is equal to the product of the, let's say, probabilities, which is replaced by the asymptotic density of the sets with exponent from epsilon 1 to epsilon n. Now, this is the main definition. What we are going to do in this presentation is to study the structural property of families which are independent with respect to the asymptotic density. First of all, we didn't have 0 and 1 in property number 1, only because if you had a set with asymptotic density 0, then of course here you will have 0 and here you will have 0. So in any family, you can add a set with density 0 and this property is always verified. And we removed 1 for the symmetric reasoning. And lastly, the second property here, algebra generated by A is included into calligraphic D, has only one meaning, that if you want to compute this intersection, then it is well defined. You can compute it. So the intersection is inside the family calligraphic D. So the density of that intersection exists. Okay. Now, one connection with the classical independence. First of all, if we take a family script A, family of subset of naturals, then of course, directly from the definition, the one that we just gave, the independence, implies the classical independence. This is stronger, because in the classical independence, we just require that all the possible intersection, whatever is the exponent, is infinite. While here on the left, we are quantifying how large is the possible intersection. What about the opposite? Well, written in this way, the opposite is false. But we can construct a D-independent family on the left, starting from an independent family on the right. How do we do it? Well, if we start with a family script A, which is independent, let's remember it means that all the possible finite intersection, whatever is the exponent, is infinite. Then we can pick some consecutive intervals of naturals which are sufficiently large. And on each of them, we divide it into some subintervals. And these subintervals are translations of multiples of 2 to the power of m. So at this point, we define a certain, for every index alpha and for every integer m, we define this set here as alpha m to be the set of, let's say, finite sequences of 0 and 1 of length m, for which this sum is odd. And you can check it that with this definition, if you define b alpha, if you define b alpha in this way, so we have all the elements which are well defined here. For every alpha, we define this b alpha. Then we can check that this b alpha has the same cardinality as the original independent family, and it satisfies the stronger property of the independence. Well, this is just a connection between classical independence and something which is stronger. First question that we may ask: what is the range of possible D-independent families? So what is written above shows that if we start with a family script A independent, then we can construct a family D-independent which has the same cardinality as the original family. But we already know that there exists an independent family of cardinality C. So the first thing that we know is that there exists a D-independent family of cardinality C. But what about the values? All the possible values, density of A, where A belongs to the family script A. Can be whatever we like, or are there always the open interval 0, 1? Can we have some holes? And this is our first result. Our first result is, let's pick a sequence indexed by C, the continuum, in 0, 1, the open interval 0, 1. Our first result says that unconditionally, means without any axiom, then there exists an independent family with respect to the asymptotic density of cardinality C, and for which the density of A alpha is equal to P alpha for every alpha smaller than C. So, in practice, a D-independent family can have as a range, with respect to the asymptotic density, any subset of 0, 1 that you like. As a corollary, well, choose P alpha equal to 1 alpha for every alpha. We can do it, because we didn't say that the P alpha are distinct. So the first corollary is that there exists a D-independent family such that it has cardinality C, and moreover, all the sets have, let's say, probability 1/2 for every element of the independent family. Now, this corollary was already obtained some years ago by Frankiewicz and Jurecko, and their methods were completely different. Okay, so now we know that the possible values of the independent families with respect to the asymptotic density are whatever we like. But we want to ask the same question for maximal D-independent families. What is a maximal D-independent family? Well, if you start with an independent family, then it is said to be maximal, and this is the definition that we all know, if it is not properly contained in another D-independent family. So maximal with respect to the partial order of inclusion. Okay, with this definition, we can describe this cardinal ED, which is written in blue, which is the least possible cardinality of a maximal D-independent family of natural numbers. Second theorem. Of course, before we read the theorem, a maximal D-independent family exists because if you take an arbitrary D-independent family, maximal or not, then you can extend it to a maximal D-independent family just using the third lemma. Because if you look at the definition of D-independence, then all the properties relies on finite operations. So you can use the third lemma. Second theorem, this cardinal ED is at least Aleph 1. So for sure it is uncountable. And at most, well, what is written here on the right is trivial. At most is the cardinality continuum. But what is interesting is that in addition, consistently, so there exists under some model in ZFC, so adding something else, it is consistent that ID, this cardinal here, is strictly bigger than Aleph 1. Of course, if here we use the continuum hypothesis, then that's false, because with the continuum hypothesis, these two cardinals are equal. So everything else would be the same. Corollary. So let's see this theorem above and the theorem below. In the theorem above, we say that we can construct an independent family with the range, whatever we like. But we can extend it to a maximal independent family, so there exists a maximal one where the range is precisely the open interval 0, 1. Does this conclusion hold for every maximal D-independent family? And the answer is, well, we don't know precisely for now, and that's the following. Let's fix a subset of 0, 1, which is non-empty. Then there exists a maximal D-independent family with cardinality continuum, and there exists a countable subfamily of B, at most countable subfamily of B of A, such that the ranges of A minus B is exactly the set that you like. And the set of accumulation points of this countable set is included into is either 0, 1, or both, or that's empty. In particular, this means what is written in purple, that the range of a maximal D-independent family is equal to the set that you like modulo countably many values. But we would like to choose beta equal to the empty set, so we would like to erase this modulo countably many values. Is it possible that for every S, we can find a maximal D-independent family where the range is exactly S? Well, the answer is positive under some additional axiom. So let's assume the Martin axiom. You can assume something less than the Martin axiom. And this is implied by the continuum hypothesis if you prefer. But the conclusion is that under this additional hypothesis on ZFC, then for every S, there exists a maximal independent family where the range of the maximal independent family with respect to the asymptotic density is exactly the set S that you like. Corollary, As a consequence, if you choose S to be the singleton which contains only the number 1/2, then there exists a maximal D-independent family such that every element has density 1/2. And that's not trivial, meaning that even if you know that there exists an independent family where all the values are 1/2, when you extend it using the Zorn lemma, it is not obvious that you preserve this property, that all the values are still equal to 1/2. First open question, and at the end, I will tell you some additional open question. Is it consistent that this last corollary fails in ZFC? So do we need some axiom here on the left? That's basically the last slides before the open questions. There are three theorems, the last three theorems, and the first one is that unconditionally there exists 2 to the C maximal in D independent families, such that all of them have cardinality C, and all of them have ranges of value which are pairwise distinct. And there are really a lot. In particular, that's not written here, but if they are all distinct, then this maximal D-independent family cannot be the same one. So in particular, there exist exactly 2 to the C maximal D-independent families, which is the maximum possible cardinality that you can get. The last two results are similar in spirit. The first one is that you can construct a maximal D-independent family without the break property. What does it mean without the break property? That a family of subset of the naturals can be seen as a subset of, I write it here. A is a subset of the power set of n, but the power set of n can be seen as the Cantor space. So we identify the power set of the naturals with 0, 1 to the power of n, which is the Cantor space. So our family script A is a subset of the Cantor space, so it has a topology, it has its complexity. And we can speak about measurability, about weight property, being analytic, whatever we like. So let's remove this one. Unconditionally, there exists a maximal D-independent family without the Baire property, and under some additional axiom, also here we don't know whether we need it or not, there exists a maximal D-independent family which is not measurable. Measurable with respect to, let's say, the Lebesgue measure on the Cantor space. Or if you want, the product measure of 1/2, 1/2 on the power set 0, 1. I conclude with the three open questions. First of all, does there exist, okay, I already told this one, without Martin axiom or something a bit weaker, does there exist in ZFC a non-measurable maximal D-independent family? We expect that the answer is yes, because this is just the analog of an ultrafilter, and an ultrafilter usually has all the ugly properties that you like. And other open question, is it true that every possible, so all of them, maximal D-independent family does not have the Baire property? And so in the screen you can see the theorem and the open question. Is it true that every maximal D-independent family is not measurable? We don't know what are the answers to these questions, and if you want to give a try, we will be happy. Thank you.
Thank you, Paolo. Are there any questions from Zoom for our speaker?
Hi, Paolo. This is Salvo. Hi, Mel.
Hi,
Ciao,
Salvo.
Salvo.
I guess you know my question. Have you already tried to extend some of these results to other densities?
No. No, we didn't try because, well, this is the first example to try. After this one, we can try other type of densities or whatever we like, replacing the, well, I think that the general problem would be not speaking about densities, but replacing D with this D here in the main definition with a finitely additive probability measure on some algebra. Well, in this case, the domain D is not even an algebra, so if you want to do it more generally, well, first of all, the most natural analog would be in finitely additive probability spaces, and then maybe let's try the densities that you have in mind. I know what you have in mind, but no, we didn't try. So, for instance, with the
Thank-
Banach density, we don't know.
Thank you.
Okay. Paolo, thank you again. Our next talk
Welcome.
will be in 5 minutes.
Okay.